The original transformer paper introduced sinusoidal position encodings to inject information about token positions directly into the model. But why use sine and cosine functions to represent positions? And what's the significance of this 10,000 magic number? Later, the authors of rotary position embeddings proposed a different idea. They encode position by rotating token representations in a 2D subspace. But how does rotating a vector encode positional relationships? These are the questions that we'll explore in this two-part video. In the first part, we are going to break down sinusoidal encodings and also talk about absolute learnable position encodings. The second part gets into relative encodings, rotary position encodings, and we'll understand the motivations and intuition behind each of them. So let's get started. First, let's quickly review why positional information is necessary in transformers. Take the sentence, "My daughter called her brother," as an example, and assume for simplicity that each word corresponds to a single token. Unlike RNNs, which process tokens sequentially and naturally keep track of order, transformers process all tokens in parallel. In self-attention, each token attends to itself and to every other token. So the representation of my is computed by attending to all words in the sentence, and the representation of brother is also computed the same way. This allows the model to build rich contextual embeddings. But here's the problem. Because the computation is entirely parallel, the model has no inherent notion of order. If we swap the positions of daughter and brother, the meaning of the sentence changes completely, but the token representations would remain identical. Even swapping my and her would produce the same set of representations. Without positional information, all permutations of the same set of tokens would look identical to the model, even though their meanings differ drastically. This permutation invariant nature of self-attention is exactly why we need an explicit mechanism to encode the position of each token. The first idea that usually comes to mind when thinking about encoding positions is, why not just use the token index? But as sentences grow longer, these positional values grow as well. That means we'd be combining relatively small token embeddings, which have small normalized values, with potentially large positional numbers. The positional signal would overpower the content signal. So we need positional encodings that stay bounded in magnitude, staying within a reasonable numeric range. Alright, so maybe we normalize the index by dividing it by the sequence length. That gives us a positional value between 0 and 1. But now we run into another issue. If we want the model to learn patterns from positional encodings, the encoding should be consistent across sequences, regardless of their length. A position value of 0.5 should mean the same thing across different sequences. However, with this normalization strategy, in our example sentence, the value 0.5 corresponds to the third position. But in a longer sequence, the same value of 0.5 corresponds to the sixth position. This positional representation strategy is not consistent across sequences, so even this approach fails. To solve these issues, and to allow positional patterns to generalize across sequences of different lengths, the authors of Transformer paper introduced sinusoidal positional encodings. At first glance, this might feel like a huge conceptual leap. A moment ago we were talking about simple integers, and suddenly we have jumped to sine and cosine waves. And that reaction is completely valid. It does feel abrupt. But once we break down what sinusoidal encodings actually do, we'll see that they are not some random trick. In fact, they are surprisingly similar to an encoding mechanism that we have all used, and more on that later. For now, let's actually dive into this sinusoidal position encodings and understand what's happening behind the scene. For the moment, we'll only focus on the sine portion of the expression to build intuition. Here, pos is the position of the token in the sequence. D model is the dimensionality of the positional embedding. I indexes the dimension and runs from 0 to d model by 2 minus 1. Each value of I corresponds to one frequency of the sinusoid. Let's interpret what this actually means. When I equals 0, the denominator becomes 10,000 to the power 0, which is 1. So the first dimension is simply sine of position. When I equals d model by 2 minus 1, the exponent 2i by d model is just under 1, giving us a denominator just under 10,000. And we can think of it as 10k for simplicity. So the final dimension looks like sine of position divided by 10,000. This means the argument of the sine function is scaled by factors that grow exponentially, from 1 in the first dimension to roughly 10,000 in the last. But how do these scaling factors affect our waves? Scaling the input to sine function directly affects the frequency of the resulting wave. With a scale of 1, we get the standard sine wave with a period of 2 pi. With a scale of 2, we get sine of position by 2, which has a period of 4 pi. Scale of 10 gives us a sine wave with period 20 pi, and with a scale of 10,000, the period becomes 20,000 pi, meaning the sinusoidal waves repeats only after roughly 63,000 position steps. So as the scale factor increases, the oscillations become slower and the frequency decreases. Now think in terms of how sensitive these waves are to changes in position. In the early dimensions, where frequency is high, even very small change in position, like going from k to k plus 5, produces very different sine values. So these dimensions can encode fine-grained local positional differences. In the later dimensions, where frequency is extremely low, positions like k and k plus 200 can still produce similar values, which means these dimensions can encode coarse global positional structure. Since each dimension corresponds to a sine wave with a different resolution, a single position gets mapped to a vector that combines local and long-range positional information across different dimensions. Earlier, I mentioned that sinusoidal encodings resemble an encoding scheme that we already know. That encoding scheme is how numbers are encoded in binary. Let's take a quick detour to binary representations. We'll write our number in decimal form, and next to it, we'll show its binary representation. Now imagine treating each bit position, that is each column of the binary representation, as a separate dimension for encoding that decimal value. Notice what happens. Each bit oscillates between 0 and 1, but at different frequencies. The least significant bit flips every step, 0 to 1, 1 to 0, 0 to 1, and so on, and it has the highest frequency. The next bit flips every 2 steps, the next every 4 steps, and so on, with frequency decreasing as the bit's significance increases. So even binary encoding is built on the same core idea. Different dimensions change at different frequencies. The only distinction is that binary encodings change discretely, whereas sinusoidal encodings change in a continuous manner. So why not just use binary? To understand that, consider a 3-bit binary encoding for numbers 0 through 7. If you plot these 8 binary vectors in order, that is from 000 to 111, the sequence does not trace anything that resembles a smooth continuous curve. Adjacent binary representations can differ in multiple bits simultaneously. For example, going from 3 to 4 flips all 3 bits. What we want for our transformer model is a positional encoding that changes smoothly as we move from position t to t plus 1, allowing the model to learn meaningful patterns from these transitions. Sinusoidal encodings provide exactly that continuity. The encoding scheme gives us a smooth curve, and the encodings for different positions is just discretization of that curve. We also saw how different sinusoidal dimensions capture different ranges of positional variation. High frequency dimensions capture fine and local differences, and low frequency dimensions capture long range structure. Binary also follows a very similar principle. For distinguishing numbers that are far apart, the more significant bits dominate. For distinguishing two nearby numbers, the lesser significant bits matter most. This pattern of local versus global information distribution is the same as sinusoidal encodings. Only difference is that the transitions are discrete. A more intuitive analogy for this is clock. Think of early dimensions, high frequency sinusoids, as the second hand, middle dimension as the minute hand, and the lowest frequency dimensions as the hour hand. The second hand moves rapidly and captures tiny differences. The minute hand captures medium scale differences, and the hour hand is going to capture long range differences. As time differences grow larger, the fast moving components, second hand becomes less useful, and only the slower coarse components, hours and minutes, matter. Sinusoidal encodings achieve this same multi-scale representation, but with smooth continuous transitions that our neural networks can easily learn patterns from. Okay, hopefully by now you have some sense of why encoding positions using sinusoidal waves isn't some random trick. Let's move to another detail of this encoding expression, the magic number 10,000. Why 10,000? To understand this, let's start by plotting the encoding values for different positions for a 256-dimensional sinusoidal embedding. Now here we are not interested in this plot on its own, rather we'll care about how the behavior of this plot changes when we alter the scale factor. With the scale factor of 10,000, which is the default value, in the later dimensions, say dimension 200 to 255, the sine waves oscillate very slowly. Because their frequency is so low, their values don't change at all for position 0 to 1000. Once we change the scale factor to a very small value, say 100, we are basically increasing the oscillation frequency of all dimensions. On the other hand, when we increase scale factor to a really high value, now the frequencies become much lower. This change is also visualizable in the plots. With 100 as the scale factor, even the later dimensions have high oscillation frequency, causing values to be distinct for even positions that are not that far apart. With really large scale factor, because of oscillation frequencies of dimension reducing, a lot of dimensions almost have the same values for all positions from 0 to 1000. So with really small scale factor, we lose the ability to encode broad global positional relationships. And with really large scale factor, the model loses sensitivity to local positional differences. 10K is actually a sweet spot where earlier dimensions cater to local positional differences and later dimensions capture long range positional differences. Another way to understand this is to compute cosine similarity between positional embeddings. Here we are taking the last 128 dimensions of the encoding at position 500 and comparing it with the last 128 dimensions of the encoding of all other positions. With a small scale, similarity drops too quickly. Even moderate position differences produce unrelated embeddings. With 10,000, similarity decreases smoothly with distance, the ideal behavior. With really large scale values, similarity barely changes. Even a difference of 1000 positions almost looks the same. Now, what about local positional differences? Since the frequency of oscillation decreases as dimensions increase, to understand how well the encoding captures local differences, we can actually look at the cosine similarity values of the first 128 dimensions. These dimensions should decorrelate quickly for significant positional shifts. With too small a scale factor, similarity collapses to zero, even for small differences, like 10 positions, so too aggressive. With too large a scale factor, embeddings stay highly similar even for differences of 50 positions. With 10,000, similarity decreases gradually and smoothly from distance 0 to around 50. This is perfect for capturing local positional differences. So it makes sense to use 10K as the default scale factor, which probably was just a result of experiments and the fact that with 10K, the longest period is 20,000 pi, which is about 60,000 tokens. So it provides a meaningful variation across large context lengths. Furthermore, it gives us a multi-scale hierarchy. Early dimensions have high frequency and hence encode local positional differences. Later dimensions have very low frequency and hence encode coarser long-range structure. We now come to the final question in the sinusoidal position encoding section. Why include cosine at all? Why not just sine? The primary reason is that using both sine and cosine allows positional embeddings to have a simple linear relationship across positions. Imagine a sentence where a subject and its verb are always separated by k positions. If the positional embedding at position pause plus k can be obtained from the embedding at position pause using some linear transformation, then the attention layer can learn that transformation through its QKV weights, making it easier for the model to detect such patterns. Okay, But how does cosine give us this linearity? To see this, we need to recall 2D rotation matrix. A 2D vector of unit length at angle theta can be rotated by angle phi using this matrix. Even if this matrix is unfamiliar, you can verify it using the addition formulas for sine and cosine to convince yourself that this is indeed correct. In the transformer positional encoding, the ordering of sine and cosine is swapped, so we effectively use a transpose of the standard rotation matrix. So if we establish our positional encoding scheme as alternating sine and cosine waves, then notice that the arguments to these sine and cosine functions are actually just angles. So pos times this entire factor is an angle. Pos plus k times this entire factor is also an angle. And when you compare each pair of dimensions for pos and pos plus k, you will see that the latter can be obtained by rotating the former by an angle of k times factor, where the factor is dependent on the dimension. The transformation that takes us from pos to pos plus k embedding is then just this matrix, which is obtained by stacking all these 2 cross 2 blocks diagonally. Each diagonal entry tik is the 2D rotation matrix for rotating by k times the factor for the pair of ith dimension. If this is the first time you are seeing this rotation matrix, then you might not understand all this completely, but it's okay. For sinusoidal embeddings, the only takeaway you need is that cosine is included so that each positional shift corresponds to a simple linear transformation, making positional patterns easier for the model to learn. That is all that we'll cover about sinusoidal embeddings. The sinusoidal embeddings used in the transformer paper are absolute fixed positional embeddings. Fixed because each position's embedding is deterministically computed and not learned during training. Absolute because the embedding assigned to a position depends only on that position index, not on the content of the sequence or the relative distance between tokens. But we can also use learnable absolute position embeddings, where we assume a max context length n and create a learnable weight matrix of shape n cross d. Each row corresponds to the positional embedding for a specific position index. These vectors will be randomly initialized and the model will learn them during training. Several models after the original transformer paper, such as BERT, GPT, and even Vision Transformer, adopt this approach. Now that we have an absolute position embedding, how do we feed this information to the model? Typically, we associate positional information with tokens by adding the positional embedding to the token embedding at the input of the first transformer layer. So for token I, its representation becomes EI plus UI, where EI is the embedding of the token and UI is the positional embedding. To see how this positional and token embedding interact with each other, let's look at what happens to the dot product between the query representation of the ith word and the key representation of the jth word. The ith token's representation would be word embedding EI plus position embedding UI, and the jth token representation would similarly be embedding EJ plus position embedding UJ. Then to get key representation, we would simply use our WK weight matrix, and to get query, we would use our WQ and then transpose of query, which would effectively be this. Now we can decompose this entire term into 4 separate terms. The first, which corresponds to content-content interaction, determines how much token I should attend to token J purely based on their semantic embeddings. The second is content position interaction, which decides how much token I's content should attend to the fact that token J is at position J. The third is similar, just flipped. How much the position of token I influences its attention to the semantic content of token J. And the fourth is purely positional based interaction. This component depends only on positions I and J, independent of their token representations. This is important because it gives the model a way to explicitly capture absolute positional relationships between position I and J. This decomposition isn't crucial for absolute embeddings, but it becomes very important when we discuss relative positional embeddings in the next part. So I thought to just introduce it before ending this part's video. The goal of this part was to ensure that you have a complete, clear understanding of sinusoidal position encodings. The transformer paper used sinusoidal embeddings for 1D token positions. Image transformer often use sinusoidal encodings for 2D spatial grid positions. And video models frequently combine 1D temporal and 2D spatial sinusoidal encodings. Sinusoidal embeddings also appear in diffusion models like DDPM, where they are used to encode time step information. Hopefully, everything that we covered gives you a much stronger and intuitive understanding of positional encodings. Thank you so much for watching this one, and see you in the next part.